In class today we started with a simple exercise. We have the shape here, the truncated prism, and so okay, here's a vector along this edge of the top, okay? And along this edge, here's a vector. Okay, we see that this vector is a little below horizontal. This vector is significantly above horizontal, but less than 45 degrees, more horizontal than vertical. Well now, if this is the positive x direction, then we ask, okay, give me a vector as multiple of sum of multiples of the I, j, and k vectors that might represent this, okay? And of course the y direction would be this way, so similarly a vector that might represent this in 3 dimensions. Again, a sum of multiples of I, j, and k. Then the question is, find a vector normal to the tangent plane. Now, tangent plane would be the plane that you get by laying something flat on top of this shape. So it should be a straightforward exercise because people have done this WebAssign, they've done these problems, gotten them right. Don't seem to be having a lot of trouble with them. But we ask for this, okay. And then we go on and ask for some other things that are related to the homework on directional derivatives. It became clear that even though people were doing well in WebAssign homework, doing well in their assignments, people didn't know what the definition of I was, or j, or k. Didn't know what the definition of dot product or cross product was, and weren't able to answer these questions. This led me to the conclusion that people are doing their WebAssign homework by following formulas they don't really understand. And there's very little geometric understanding behind any of this, and this is a very geometric course. So we spent the time just working out a few simple things, just based on those few questions. And we needed to spend the entire time. Now, I'm not saying there's anything wrong with the class or with the students. You're doing what WebAssign asks you to do, and I've never been under the illusion that WebAssign really does the whole job, okay? Now, I've been lecturing, I've developed these concepts, everything that we talk about here, we've done, and I think it's been done pretty clearly. You can go back and look at videos and see. But between the fact that people are not understanding the concepts behind the problems and not applying the concepts, but just applying the expedient solution of following some kind of a formula, and by this time people have used probably over 100 formulas that they're not going to remember for the test, and haven't developed the geometric intuition. It becomes clear to me that the lectures I've been giving, or the class time, hasn't been productive. Okay, so we're changing the way the class runs. And I'm going to turn you loose in WebAssign, but with the advice to read the text and try to get to the principles behind everything that you apply to the problems. Don't just be satisfied to get the right answer on a problem. Don't be satisfied until you understand the problem in such a way that if the book was taken away from you and all the formulas were taken away from you, you could still solve the problem, but without having to memorize 100 formulas. Okay, so anyhow, let's see what we're doing here. First of all, people didn't know the definition of dot and cross product. So I tried to drag that out of people, but nobody knew this, nobody knew this. Okay, they kind of knew that the right-hand rule had something to do with it, and kind of know how to do the right-hand rule for I cross J and J cross K and so forth. So that's a start, but people weren't applying the right-hand rule now to the vectors we have here, a vector in this direction and a vector in this direction. You put your fingers in the direction of this vector, and you turn your palm so that when the fingers curl, they point in the direction of this vector, and there's your direction of your normal vector. And of course, the magnitude of the normal vector is here, and I'm not going to read these formulas to you. A little fuzzy on the idea, how do we determine, okay, the first answer I got on how do we get the vector perpendicular to these two vectors, the dot product. Well, that can't be the answer if we understand anything about the dot product. It's that it's a number, it's not a vector. If we understand anything about the cross product, it's that it's a vector and not a number. Okay, so this is a number, this is a vector. These are fundamental concepts that should be completely intuitive by now. Again, I'm not saying there's anything terribly wrong with people for not knowing these things, but it's going to be necessary when there's a midterm test coming up soon that these concepts be well established. Okay, so I want people to think about how to approach the course so that essential things like this don't go away. Okay, we build on them, we keep building on them. Everything in the class builds on concepts that we've had previously. Okay, so anyhow, there we have it. So we come to the conclusion that to get a vector, a normal vector, what's a normal vector? It's perpendicular to the plane. I haven't written this down, but what do we mean by a vector perpendicular to the plane? And people couldn't give me a real good answer to that, but there's some, people were kind of close. They said something about perpendicular, but never really got to the statement. And there are many equivalent statements, but the vector would be perpendicular. The normal vector is perpendicular to every line in the plane. Now, I prefer that it's perpendicular to every vector in the direction of a line in the plane, because then you're talking about being perpendicular to a vector, and there's a very simple criterion for being perpendicular to a vector, that the dot product would be 0 because the angle is 90 degrees, cosine of 90 degrees is 0. Okay. Also, as we've said, if you have the two vectors that we demonstrated here, the one here and the one here, you take their cross product, then you have a vector perpendicular to both of those vectors. Okay, because the basic idea of the cross product, part of the basic idea is that it's perpendicular to both vectors. And you look at the parallelograms and parallelepipeds and the volumes and stuff like that, and you really understand those things so that you understand the nature of the dot and cross product. Okay, and those problems were there in WebAssign, and again, they got done correctly, but nobody really understood it. Because again, well, let's see. Okay, so, okay, there we go. Now, the normal vector is perpendicular to every vector in the plane. If you take the cross product of any two non-parallel vectors in the plane, then you get a normal vector, a vector normal to that plane. Now, I say vectors in the plane. Vectors don't have locations. Vectors are displacements, or vectors, well, they're other things besides displacements, velocities, accelerations, electric fields, magnetic fields, and so forth. And they generalize even more than that. But using the concept that the normal vector is perpendicular to every vector in the plane, you take any two vectors in the plane, which means any two vectors parallel to any two lines in the plane that aren't parallel, any two intersecting lines in the plane, if you wish. We can conclude all kinds of things. For example, if we know two non-parallel vectors in the plane, it's easy to calculate a normal vector. That's exactly what we're talking about. Now, I make this statement And I don't go into the fine details of how you would symbolize that, because I want you to think that through. Okay, well, if we want then the equation of the plane, which is the next thing we ask, the equation of the plane tangent to this surface, okay, we use this picture, which I made a big deal of, well over a month ago, close to 2 months ago, that the point x naught, y naught, z naught is on the plane perpendicular to the normal vector ai plus bj plus ck. Now, we talked, I had this picture without the arrow drawn here, and asked, okay, what's the criterion for x, y, z to be on this plane? Okay, without that arrow there. And it should be obvious from the things that we need to understand at this point, that we needed to understand at a point 6 weeks or more earlier in the course, that the vector from here to here has to be perpendicular to the normal vector. Okay, the displacement vector between 2 points in the plane is perpendicular to the normal vector. Okay, this is a vector in the plane, or a vector parallel to a line in the plane, provided x, y, z is in the plane. This point's in the plane, this point's in the plane. So this vector is parallel to a line in the plane, has to be perpendicular to the normal vector. It took us a long time to get there. Okay? Now, then we symbolize this. Okay, first of all, this vector from x naught, y naught, z naught to x, y, z has to be perpendicular to the normal vector. Well, how do we symbolize the vector from x naught, y naught, z naught to x, y, z? Okay, not everybody got this, but some people did. It's x naught, x minus x naught I plus y minus y naught j plus z minus z naught k. If you don't understand, you really need to ponder this. Because again, it's fundamental of what the first thing you do with vectors almost. So now we have a symbolic representation of the vector from here to here, which has to be perpendicular to this one. Now, next statement that we might want to write is, well, now this vector has to be perpendicular to the normal vector. And that means that the dot product is 0. There's another step. People weren't able to make that step. Okay? Two vectors are perpendicular means the dot product is 0. We just write this out. And then we do the dot product, which again caused a problem. But we eventually found that the dot product was this, and this equation then tells us this, and this is the equation of the plane that people probably use in answering questions in WebAssign about the equation of a plane. People use this without thinking any of this. Okay, you really don't want to be using formulas without thinking about what they mean and the picture and the basic concept behind the formula. Because there are many formulas, many forms of the formula. You're going to memorize every form, okay? And also, if you just use the formula, you're not understanding what it means. You're just getting the right answer. Okay, well, we're going to work on meanings, okay? I could say more about this, but the reasoning from here to here in this picture, it's in your textbook, it's in every textbook I've ever seen, not in every multivariable calculus textbook. It's a picture that needs to stick in your brain, and also the picture of the equation of a line, and all the other pictures that bring this stuff together in a way that allows you to solve problems rather than imitate formulas that you might have in front of you when you do the homework. So when you do the homework, you shouldn't be doing a formula search. You shouldn't be you shouldn't even have your book open. Learn the stuff. make notes, then go to your homework. Now, if you have to look something up, okay, but if you have the formulas in front of you, you're not likely to think. Not likely to think about what anything means. You should also have a notebook of these important concepts, these important ideas. So what, the plan for the course is going to turn you loose in WebAssign. Prefer that you figure it out by reading and do the homework without the text in front of you. But one way or another, get it done, and then we'll come to class and we'll work on the meetings. And that's what we're going to focus on. Why did this thing that you did for homework, and under time pressure, I certainly understand, by the most expedient method, why would you use that method? What does that mean? How does this relate to the overall picture of the course, which is very geometric? Okay, well, again, I'm not taking people to task for what we're finding here, just explaining how the approach people have been using isn't really working very well. Now, you still have a foundation. You've still thought about things. Hopefully, in the next couple of weeks, we can bring everything together in a nice geometric picture where there's only half a dozen ideas that you have to remember, and instead of hundreds of formulas. And having done that, you'll be in much better shape to solve problems on an exam. And that's not the bottom line, because, of course, people in this course are aiming at an engineering curriculum, and this is the language of much of engineering. If you don't understand the meanings, you're not going to be as likely to understand the engineering. You might be able to do the calculations, but you're going to be better engineers if you do a little more than just calculate, okay?